Welcome back to the lecture on spectroscopy, the introduction to molecular spectroscopy and chemistry 2. This is a very short lecture on an important quantitative law known as the Beer-Lambert Law, which is used to study the fluorescence properties and also determine concentrations of compounds which show fluorescence characteristics in samples. Therefore, it is a quantitative law used to measure concentrations of species through fluorescence. So, basically absorption of light, absorption of visible light, and I shall just write down the law in a simple form. We will see more of it when we study electronic spectroscopy with some applications and properties of molecules and so on. In a very simple and elementary form, the Beer-Lambert law goes like this. Suppose we have light falling on a sample tube containing the sample, and let the concentration be C moles per liter, and let the length of the spectroscopic cell, the spectrophotometer, the cell with which we use to measure the absorption and also take the spectrum. This is the cell of length, say L centimeters. It is usually 1 centimeter or even less than that. And if light with a certain initial intensity I naught, visible light, falls on the sample and light with the intensity IF is emitted, obviously IF is less than I naught. Okay. That means that the sample has absorbed some light, and this phenomenon for certain small concentrations and reasonably low intensities of light absorptions, small concentration C, like millimoles per liter kind of concentrations or even less. Okay. Typical example. Okay. And then for light of moderate intensity, satisfies the law that log I naught by IF is equal to a constant times the concentration of the substance and the length of the cell, and this constant is called the molar extinction coefficient or molar absorption coefficient, and this is called absorbance. You can also write this in the form of transmitted radiation, and so this can be written in the form of light that is, this is the light that is transmitted. Therefore, this ratio, the logarithm of I naught by IF, gives a constant associated with each system, each chemical species. And one important thing is that this epsilon is actually a function of the wavelength of light, lambda being the wavelength. So, typically if a species absorbs light as a function of the lambda and you write the epsilon as a function of epsilon lambda, you choose that value of epsilon for which the absorption is the maximum. Okay. That is that value of the light lambda. So, you choose that lambda and perform this experiment, and these are tabulated in all electronic spectra textbooks and also in analytical chemistry textbooks. Now, how do we get this law? Log I naught by IF is equal to this constant epsilon times concentration and length. Okay. It's a very simple argument that if you have a cell of length L, consider a small, an extremely small what is known as infinitesimally small, dl. Because at that level you can imagine that most things will be linear. If there is an absorption, that absorption will be roughly proportional to the concentration in that region, and the absorption, I mean if there is more species, obviously there will be more absorption. That linear law can be obtained from starting with this kind of infinitesimals. Therefore, if you do that, the dl, which is also a very small length, tells you that the absorption is dependent on dl itself. If dl is slightly more absorption and so on. So what you do is you take the differential. If I is the intensity at this point and I minus di is the intensity of light that is emitted passing through dl, then you can write the minus di as roughly proportional to the concentration and proportional to the dl, and obviously also proportional to the intensity of light that falls on it. Therefore, if you write this, the linear law simply gives you minus di is some constant which I will write as say kappa, okay, some k times c times dl times I, and so you can write minus di by I is a kappa, a constant c dl. And now you extend this argument that this is what happens throughout, and therefore if we start with I naught here as the initial intensity, and if we end up with IF as the intensity of light emitted at the other side of the cell, then you know when you integrate this equation, you integrate it between the limits I naught and IF and write di by I, and write that as the length being also integrated, it is kappa times c dl, starting from the length 0 here to the length L. So this gives you immediately L and I between the limits I naught and IF is kappa c L between the limits 0 and L, and therefore you know immediately that you get Ln I naught by IF is kappa times c times L, and Ln is of course 2.303 times logarithm to the base 10 of I naught by IF, and that is equal to kappa times CL, and so you write logarithm of to the base 10 I naught by IF is equal to kappa by 2.303, which is again a constant, times CL, and this is what is called the epsilon or the molar extinction coefficient. And by dimension, please remember this is dimensionless because they both refer to intensities. So this is left hand side is dimensionless, right hand side is moles per liter, and usually L is expressed in centimeter, therefore epsilon is liter per mole per centimeter. And at low concentrations and low intensities, epsilons are additives. So if you have two substances with differing concentrations, then the absorption at that frequency of or the wavelength of light by both these substances is roughly additive, that the absorbances of the first one and the absorbance of the second one add in the logarithmic ratio, and here they add in terms of the concentration times the molar extinction coefficient. Some small numerical problems will give you how to do this in a and how to do this for different concentrations, and also sometimes determine the unknown concentration of the substance that you want to find out by a fluorescence experiment. This is an important tool and we shall see more of it, but I just wanted to introduce this as something to remember before we do the electronic spectroscopy. From the next lecture onwards, we shall start with the microwave and then the vibrational and the electronic spectroscopy, and also talk about the molecular properties like the dipole moment, the polarizabilities, the moments of inertia, as we start looking at microwave spectroscopy. There will be some numerical problems given on this in some of your assignments, okay, to make you familiar with some of these elementary concepts. Okay. We will continue this with the subsequent lectures on rotational spectroscopy. Until then, thank you very much.